So the inversion is pretty straightforward. Say f of t, we have to get back what f of t is, which was basically what we defined at the start. Well, let's assume we don't know what f of t is. Let's just call the inverse f of t at this point. Formula for inversion is 1 over 2 pi I integral over some Laplace contour of e to the capital St, capital F of s, d of s. Now we have to define what L is, and for that reason we need the region of convergence. So I'm going to just draw this quickly. So assume, maybe I'll use white here. Assume you have your axes in the complex plane, in the complex S plane to be precise. So this is imaginary, this is real, that's fair. And now our contour, well, we have the real part of S is greater than 0, so we can't really touch 0. The real part of S equals 0, which is the imaginary axis, we can't touch that. So we have to always be on the right hand side of the imaginary axis. This is L. But for the sake of integration, we need to close this up like this. If we go back, we have to sort of loop around, and I'll explain why. We come here, and then similar kind of symmetry on this side. Not the best contour I've ever drawn, but I think this works. There we go. The arrows for the orientation, the direction. Now the real reason why we omit the 0 is because the natural log has a branch cut. So I don't know if you guys have watched my video before about multi-valued functions. This is an essential idea that I will employ. So I use sort of a dashed line for this. So that in red is a branch cut. So you can't really cross it because the natural log is a multi-valued function. We have to avoid the branch cut as much as possible when we're integrating, especially. So for that reason, I'm really avoiding it because I don't want problems to happen. Plus natural log at 0 is also undefined, so we don't want to unnecessarily have problems there. That's like an implicit pole built into all of this. Okay, that's fair. We can label this is L. We already labeled that. Segment 1. I don't want dotted lines. Segment. So yeah. So this is segment 1. This is segment 2. Circle segment 3, segment 4, and then segment 5. Well, we already proved in a more general sense in the previous videos that integrals over segment 1 and segment 5 will all go to 0. So I'm just going to omit them. I'm going to work with segment 2. So for segment 2, we need to parameterize everything in a certain way. So the parameterization that works is S equals R e to the I theta. But the thing is, we need to choose theta properly because theta is constant on that entire horizontal line. Now, one way of doing this in this way is really powerful, is looking at the phasors with respect to what we avoided or the branch cut. So if we like make the branch cut our origin, we don't really need to explicitly do that because the branch cut is 0, i.e. the origin. Then we are on this part of the plane. The angle on this part of the plane, if you want to consider everything in an anti-clockwise sense, this is going to be positive pi. So our theta is simply positive pi. That's the wrong orange. Okay. So if we do that, we have ds is r dr e to the I pi. Yeah, let's just keep it there. I'm not going to write it as minus dr. It's understood. Now if we do that, if we plug that in, we have 1 over 2 pi I integral. We're going from infinity to 0. Now notice this is not really negative infinity because we accounted for the sign in this angle in the phase. So all we care about is the magnitude now, because dr or r is the magnitude. So the magnitude itself is going from infinity to 0. This is a difference here. This is different than what the regular complex analysis. It's the complex analysis of multi-valued functions. So we have this setup. What else? We have e to the r e to the I pi t, and then all of this over r e to the I pi minus Euler-Mascheroni constant. We probably need a little more space here. Maybe I'll just move everything down. Minus natural log of r e to the I pi dr e to the I pi. Things are gonna cancel out, this and that. We can sort of suck out the negative and then use it to flip the bounds. E to the r, we can just use a minus here. E to the minus rt. Euler-Mascheroni plus natural log of r plus I pi dr. Let's just keep it right there. Oh, we have to divide by r. I forgot that. Let's just keep it right there. We can't really do much at this point. Let's just keep it there in the hopes that it might cancel out with segment 4, which is its sort of antipodal partner in a way. So it's a hard time selecting what color I have to use. So now for segment 4, we have to proceed in a similar way because again it's symmetric. S is r e to the I some angle. Now what angle? This is really important. We're here on the plane, but we can't really cross. We can if you want to rotate and if you want to conclude that this is well, pi again or whatever, because it's the horizontal part of that. Well, you're wrong, because here's why. There's actually a branch cut right here, right? I mean, you can see it in the diagram here. It's pretty evident. There's a branch cut there, so you can't really cross it when you're rotating, because you're gonna go on a different Riemann surface, and that's gonna really mess you up. So the angle here is considered by doing an anti-clockwise rotation. So with a minus pi, you have a minus pi here. Everything else is essentially the same. We have dr e to the minus I pi. See, that's why I didn't plug in a minus right there, because both of these e to the minus I pi and I pi are minus, but it really changes the I plus I pi here and minus I pi that I'm going to have later, because the natural log is multi-valued. This is just evidence of that. So on segment 2, we have 1 over 2 pi I integral. Now we're going from 0 to infinity. We'll have e to the minus rt, because e to the minus I pi is also minus 1, and exponential itself is not multi-valued, so that we won't have problems there. R e to the minus I pi minus Euler-Mascheroni minus natural log of r e to the minus I pi, and then dr e to the minus I pi, which cancels out with the denominator, leaving us with pretty much everything else is the same. Nothing really changes. Minus Euler-Mascheroni, minus natural log of r, and now minus of minus I pi. So we have I pi with the dr. See, now the phase matters because we have a plus I pi instead of everything else is minus, and the I pi sort of remains the same. Now the beauty of this is if you add both of them together. Maybe I'll go with blue. You add both of them together. Say 2 plus 4. The Euler-Mascheroni. Oh shit! I forgot the r, didn't I? To be careful with these things. You add 2 and 4. Well, the Euler-Mascheronis will sort of go away. One has a minus, the other does not. This goes with that. The natural log itself will also go away, but the I pi's will remain. So I pi and I pi, we have 2 I pi divided by 2 pi I, integral from 0 to infinity of everything else is the same, e to the minus rt over r dr, I believe. Yes, this becomes 1, integral from 0 to infinity e to the minus rt over r dr. Well, now in the conventional sense this is diverging, but don't worry, we have segment 3 to worry about, which should eradicate the divergence issues in the asymptotic limit at least. Okay, so now we have to parameterize part 3. Part 3, segment 3 is a circle. So only thing that's changing here is the theta, the phase. The radius is relatively constant, and as convention dictates, we're going to call it epsilon, e to the I theta. We had a dr before because the radius or the magnitude was changing, the phase was constant on those horizontal segments. Now our theta is going to change while epsilon is going to be constant. So ds is just going to be epsilon I e to the I theta d theta. Okay, so all we have to do is just plug this in. We will have 1 over 2 pi I. Well, a circle is like this. Oh, that's horrible. It's like this. Here we decided we had a positive pi and a negative pi. So we're going from positive pi to negative pi. And we have e to the st, so that's epsilon e to the I theta times t divided by s, which is epsilon no I there, e to the I theta minus Euler-Mascheroni minus natural log of s, which is epsilon e to the I theta. And now we're going to have epsilon I e to the I theta d theta. This cancels with that, all of that. You can use a negative to flip the signs around. We'll have a minus pi to pi. Oh, and do not forget the limit that we have to take. Epsilon goes to 0, because without this limit none of this will be possible. Like part 2 and part 4 are really close, such that they almost have the same phases. They're along the branch cut because epsilon's really small. Segment 1 and 5 also cancel because epsilon's like really small. So this is also one of the larger assumptions that we will make. And do not forget to take the limit. At least write that out. That's really helpful because it's going to cancel many things later. We have natural log of epsilon plus I theta. Yep, and we have a d theta right there. And the I we can take out, which cancels with the denominator. In the limit, this will go to 1. We will have Euler-Mascheroni times pi minus of minus pi upon integration, which is 2 pi divided by the 2 pi up front. So that will just give us Euler-Mascheroni plus limit as epsilon goes to 0 of natural log of epsilon. Well, other bit is just I over 2 pi theta squared over 2 from minus pi to pi, which will entirely just go to 0 because it's an even function. And this is what we're left with. Now this diverges, but maybe we have a hope of this cancelling out with the divergence up there that we created for 2 plus 4. So we just need to see if that works out. If it does, we should get back our f of t, which was natural log. And mind you, all of this what we're doing, this is just for t greater than 0, of course, because that's the way we decided to close these things. T less than 0 is on the other side, which I haven't really clearly demarcated here. That was again horrible. That's t less than 0. Okay, so we have to just check if everything works. So 2 plus 3 plus 4. We know what 2 plus 4 is. That's just that. Integral from 0 to infinity. E to the minus RT over R dr plus Euler-Mascheroni plus limit as epsilon goes to 0. Natural log of epsilon. This is not really L or what we want yet, but you'll see this is well connected to that. We can use some integration by parts here. Integrate over 1 over R. So you have natural log of R e to the minus RT dr, and then you differentiate the exponential. That cancels with the negative from integration by parts. We get a t. Integral from 0 to infinity. What? My bad. I have to evaluate this. 0 to infinity. E to the minus RT. Natural log of R dr. Everything else is pretty much the same. Epsilon, the exponential will dominate the natural log growth and make the entire composite function decay. So that's 0 at infinity. At 0, well, the exponential will become 1, and we'll have a natural log limit as r goes to 0 of natural log of r. Now what we can do here is like a u substitution again. So u is RT, du is dr times t. So if 0 to infinity, e to the minus u, natural log of u over t, and then du, that takes the t away, plus Euler-Mascheroni plus limit is epsilon goes to 0 of natural log of epsilon. Now we can make the assumption that, so r and epsilon rates are the same. That's Cauchy principal parts right there. Making this and that disappear completely. We just have that integral expression left out, which is similar to the Laplace transform original when we were just doing the forward transform, in the sense that we just have to split it by the linearity of the integral like this, so that we get this digamma of 1, which is minus Euler-Mascheroni, minus, I believe this will be natural log of t, and that trivial integral there, plus Euler-Mascheroni, so that cancels over here, minus natural log of t times gamma of 1. So we have minus natural log of t, but all of this added is not really L, right? Let's look at what's L. So just on the green parts, L, that's the vertical part, plus segment 1, plus segment 2, plus segment 3, plus segment 4, plus segment 5. They constitute the entire contour integral, but since the entire contour integral of the integrand, which is e to the st capital F of s, you see the pole happens at s equals 0, because a natural log blows up and 1 over s also blows up. We're avoiding that. There's no other pole. It's completely analytic. So this is 0 by Cauchy-Goursat theorem, which means L is just the negative of, we know part 1 is 0 and part 5 are 0. 2 plus 3 plus 4. L is negative of 2 plus 3 plus 4 by Cauchy-Goursat. So L, that's what we wanted, is equal to minus 2 plus 3 plus 4, integral over those bits, which we calculated to be minus natural log of t. So we just get a natural log of t. And as I said, this is for t greater than 0. That closure was for t greater than 0. For t less than 0, it's trivial. For t less than 0, there's no branch cuts, there's no poles, there's nothing. So the entire integral for t less than 0 will be 0. So we will return to what we thought was defined to be the inverse f of t. So that's when t greater than 0 and 0 and t less than 0